Good morning, friends. We are having a derivation on the inclined surface that is submerged inside the liquid. So, the equation contains the center of pressure and the total pressure. So, that is the static force acting on the inclined surface. So, the inclined surface here, so of any arbitrary shape that is submerged in the liquid such a way that the surface is making an angle theta here. So theta is the angle made by the inclined surface. So the arbitrary shaped submerged body is this. So the plane of the body is projected like this. So G is center of gravity. So that is projected on the plane here, which is at a distance h bar from the free surface of the liquid. P is center of pressure on which the total pressure force F is acting. So that is at a height of hc from the free surface of the liquid. So G is at a distance of h bar from free surface. hc is the distance of P from free surface of the liquid. P is center of pressure on which this total pressure force F is acting. So these values of h bar and hc, they are measured with respect to the free liquid surface. I have here another plane, so that is OO. With respect to this OO, that is the body is now perpendicular to the given plane OO. The corresponding points of this h bar hc will be taken as y bar and yc. So y bar is distance of G from the given plane OO, and this P is at a distance of yc, where the same distance, the same P, when it is measured from free liquid surface, it was measured as hc. Now I am considering one arbitrary element here. So at a distance y with a thickness of dy here. So let this center of gravity of this element is at a distance of y. So the corresponding point here on the plane is at a distance of h from the free surface of the liquid. So the nomenclatures used in the derivation are shown here. Y bar, yc, then h bar, hc. Then G and P, center of gravity, and P, center of pressure. Capital A is the total area of the inclined surface. Theta is the angle made by the immersed surface. OO is the plane perpendicular to the given body. Now total pressure force F. So we are considering here a small elementary area dA at a distance y and the thickness dy. Now consider the small right angle triangle here. So with the angle theta, so sin theta is the opposite side, so that is h here, and the same distance on the plane, so that is nothing but y. That means the elementary area is at a distance of y from this axis OO. So the distance from here to here, so that is nothing but y. So if I consider this small right angle triangle here, so sin theta is equal to opposite side h by the hypotenuse y. So h by y. Similarly, considering the position of G here, so considering this smaller, that is another smaller right angle triangle. So sin theta is opposite side h bar divided the hypotenuse. So that is y bar here. So sin theta is equal to h bar by y bar. Similarly, considering the next bigger right angle triangle, so this opposite side is HC and the hypotenuse here is YC. So sin theta is equal to HC by YC. So the pressure acting on the strip is now P is equal to rho GH. So that is hydrostatic law. So my H from this equation, I am considering H as Y sin theta, substituting H is equal to Y sin theta. Now that is the pressure. Now pressure force acting on the strip. So dF is equal to pressure into area. So that is dA. So rho G Y sin theta, that is pressure into area dA. Now that is the pressure force acting on one single strip. Now considering total pressure force on the whole body, F is equal to integration of dF. So integrating the expression dF, substituting dF here. So only y is the variable here inside the integration. So now integration of area into distance, dA into y. So that is nothing but my area into y bar. So that is area into distance means moment of the area about the axis OO. So area which is at a distance y here. The element is at a distance of y from the axis OO. If I consider this entire body, so the total area is now passing through this point G, which is at a distance of y bar from the axis OO. So taking that area into y bar as moment of the area. So now in equation F is equal to rho G sin theta, this integration of y dA is nothing but A into y bar. Now we know from this h bar is equal to y bar sin theta. So in place of y bar sin theta, substituting h bar, we have F is equal to rho G A into h bar. Now position of center of pressure. So we are taking now pressure force acting on the strip dF, that is equal to P into dA, which we have already written here, P into dA. Now that pressure force multiplied by the area distance now. So that is dF into y. So that gives the moment of the pressure force about the axis OO. So from the axis OO, the element is at a distance of y. So the pressure force is acting through the center of gravity of the strip at a distance of y from the axis OO. So force into distance will give you the moment. So dF into y. So now y into y becomes y square dA here. So now summation of the moments means this is moment of one single force. Now moment of total pressure, that is given by integrating this expression, we are getting sum of the moments. Now taking this integration dA y square as moment of inertia, area into distance square, integration of dA y square as IO, about the axis OO. Then taking the moment of the total pressure force, so we are taking as force into distance. So equating the two moments, we are getting this expression. Simplifying, we are getting the expression. Then applying parallel axis theorem and simplifying, we are getting the expression here. Thank you, friends.